Okay, we're back. So we're back with part two of our discussion of extended grapheme clusters. And in part one, I covered a lot of sort of theory about extended grapheme clusters, and we were looking at exactly what are they and how do you build an extended grapheme cluster out of multiple code points. And if you haven't watched that and you want context for this video, I would totally go back and watch that. Um, And today I want to talk about sort of the practical implications of extended grapheme clusters in the code for my text editor. For those of, I guess bigger context is this is part of a series of videos about a text editor I made, which is called Watt. Here it is. It's a text editor for the Mac. I've been working on this for the past 10 months or so. Um, and it's just, I'm trying to document things I've learned and also, share things with all of you out there, especially if you are you're working on a text editor yourself or curious about text layout and rendering, which I am. So we're going to talk about the code for Watt, and this is probably going to be the first video. Oh, and I should have said there's a playlist for this. So if this is the first video you're watching, you can go back and watch the first extended graphing cluster video, or you can go back to the beginning and see other things that I've been talking about. The We're going to get into the code, and this is the first time I think we've really gotten into the Watt source code, and we'll get there. There was one note I wanted to make about extended grapheme clusters that sort of a follow-on, I guess, theory note. So here we are back in Unicode Standard Annex 29 or UAX 29, which is about Unicode text segmentation, which is to say breaking code points into or grouping code points into grapheme clusters and also into words and sentences, and it's a lot of stuff. It's pretty interesting. I've probably read most of it. I don't think I've read the whole thing, and certainly not in one sitting. Um, in the last video, I was talking about defining an extended grapheme cluster as approximately, in a hand wavy way, what the user would consider one character on the screen, right? You're reading a text in some script and you're like, that's a letter. T is a letter. Um, and I mentioned something about ligatures and I didn't fully know the answer. And so I went to look it up. And of course, it is in UAX 29. And so the question is, what is the relationship between an extended grapheme cluster and a ligature? A ligature is, yeah, two letters joined together to form, some sort of single glyph. And in fact, I guess that's what it says right there. Um, the common one in English is FI. I've seen this a lot. I think it's quite pretty, actually, this sort of the way this teardrop at the end of the F and how it merges with the I. Though sometimes I do think you can misread it. It looks like an H. Anyway, the question is, what is the relationship between extended grapheme clusters and ligatures? And of course, UAX 29 has the answer. Specifically here, grapheme clusters are not the same as ligatures. For instance, the grapheme cluster CH in Slovak is not normally a ligature. Conversely, the ligature FI is not normally a grapheme cluster. What I think this means practically, which is kind of interesting, is that you can have a glyph made up of multiple extended grapheme clusters. And I think it's possible. Is it possible to go the other way around to have an extended grapheme cluster made out of multiple glyphs? Maybe not. I thought there was. Maybe I'm misremembering. But the basic idea is, well, a glyph like the FI ligature. Um, this is made out of two extended grapheme clusters, F and I, and of course they happen to be one code point. But you could have uh, uh, extended grapheme clusters in theory that are multiple code points and make up a ligature together. The reason this glyph, even though it's a single glyph, is not an extended grapheme cluster is that if you're in a text editor, you need to be able to put the caret here and here and here, right? Because you need to be able to delete the F if you want. Or I guess forward delete the I, or select only the F and replace it with something. And that is, I guess, a more, let's say, a more complete statement and a slightly less ignorant statement on my part. Default, and this is, I think, key, default grapheme clusters do not necessarily reflect text display. Um, And this is exactly what we were just talking about. Okay, so where are we going to go? We are going to go back to the Sum Tree Z article that Thorsten wrote, which is a very good article, and go back to that nice diagram of a B tree based rope, or what Zed calls a sum tree based rope, that that I didn't have to make myself. So thank you, Thorsten. And just as a little sort of reminder, you have leaves. Each leaf contains some text. You have intermediate nodes which contain no text. They contain sort of a summary of the subtree. We will ignore that for now and get to it later. We're just going to focus on the leaves. And crucially, because it's a B tree-ish thing, all the tree is fully balanced, always fully balanced, which is to say that every leaf is the same height. Every leaf has the same distance in internal nodes between the leaf and the root. So you might say the root is height 0, this is height 1, this is height 2, and then all the leaves are height 3. So what we were talking about is whether what's allowed to split, like what units of text, if you want to call it that, are allowed to split a leaf, like to start on this leaf and end on this leaf, as an example, or even start on this leaf, continue across all these leaves, and end on this leaf. In my implementation, no idea what Zed is doing. I'm assuming all text is valid UTF-8. That is checked before the data structure is built up. UTF-8 is a variable with encoding, which is to say some characters are represented as 1 byte, some as 2, some as 3, some as 4. It's actually pretty easy to understand this. If you read through the Wikipedia article and read this diagram, I think it's quite clever. It has a lot of nice properties. A code unit in Unicode language is the I don't know how you describe that. I guess it's the sort of size of integer that goes into the encoding into a specific Unicode encoding. So in UTF-8, the code unit is a byte, and you can have between 1 and 4 bytes for code point. In UTF-16, the code point is a short, or a 16-bit integer. UTF-32, the code unit in UTF-16 is a 16-bit integer, and in UTF-32, the code unit is a 32-bit integer. UTF-8 is a variable with encoding, as I said before. And so one question is, okay, so as I said in the last video, we have to make sure that we bound the length of the string in each of the leaves. And the reason is because if we were to be able to store a string of arbitrary length in the leaves, then you'd end up in a situation where you'd lose the log n access properties of this data structure, and the log n access properties, and you'd be back to big O of n. And the reason it's big O of n, not big O of 1, is because given that UTF-8 is a variable with encoding, in order to say go to the eighth code point in a string, you have to walk forward. You can't just use a constant offset from the beginning. There was something I sort of glossed over last time that I think it's useful to say specifically. The question is why do you lose the log n properties of this tree, of this data structure, if everything is stored in one leaf? And given that you're storing strings in one leaf, why is it that, and those do have, even all of these small strings in the leaf have, what is it? Even though they have order n, like, don't these still, doesn't within each leaf, don't you have order n access or order n properties? And the answer is yes, you do. But if you keep these short enough, it becomes a very small factor as compared to, the thing that dominates is the fact that in this tree, most things have log n properties. And so the way generally you do you do access, so you want to look up the millionth character in the tree, is you do some sort of log n operation that allows you to walk down to one of the leaves, and then you scan through the leaf, sequentially, um, in order to find the thing you're looking for. Um, and as long as each leaf is bounded in size, um, a sequential scan through, let's say, 500 bytes or 1,000 bytes, that's very quick. A sequential scan through many gigabytes is very slow. And so what you're sort of balancing here is the you want to store enough text in these so that you're not doing unnecessary pointer chasing where you every operation you end up following pointers to a different leaf, and or doing the whole the log n descend all over again. But you want these to be short enough so that whatever order n uh, factor comes into play when you're searching within a leaf is essentially a tiny constant compared to the overall uh, access, whatever operation you're performing. Okay, so now that I think we've sort of added a little more context and a little more meat onto um, talking about this tree or the rope, and I will make a longer video on the rope at some point, though. There are so many good resources out there now that cover the sort of basics of these that perhaps I think I'll only be talking about some things that are a little more esoteric or more specific to Watt. But going back to where we were in the last video, I was one of the things I was saying is even though these leaves store bytes, I don't allow a single code point to span to cross a leaf boundary. So you can't have like if it's a 2 byte code point, and I think like this, the E with the single code point E with a cute accent, I believe is encoded as 2 bytes. So I don't recall. You can't have the first byte at the end of the left leaf and the second byte at the end of the right leaf. And this is, this creates, I think I said this in the last video, this creates some slop, which is to say you you can't, like, depending on the code points that are in a given leaf, you maybe can't pack all the way up to the limit. And the limit in my case is 1,023 bytes. But it's okay because in the worst case you can you have a code point, the next code point takes up 4 bytes and you only have 3 bytes available, so the maximum size is 1,000, and so you lose a little bit, but it's not the end of the world. What you can't do, and again this is a review from the last video, is you can't force a character or an extended grapheme cluster to not, you can't forbid a extended grapheme cluster from crossing leaf boundaries, because extended grapheme clusters can be arbitrarily long. So you can have a string with a single character, what Swift calls a character, that is 10 gigabytes in length, and obviously then you wouldn't be working with a tree, you'd be working with a string, just a linear set of bytes. So what you have to do instead is you have to like sort of attach state and metadata to the leaves, so that when you're traversing, you also have to attach these to the internal nodes, so that when you are traversing, you know where the next character is. If I say the fifth character, you know which leaf it starts on, and then when reading out the character, you may have to read multiple leaves in order to get the full character. Now, you don't actually have to do this. There are other ways to do it, but I think what I'll do is I'll first show what I did, and really what we're going to look at is mostly just like what data is stored in the leaf, in each leaf, and then I'll talk about at least one other way to do it. Excuse me, that I know about. So let's do this. So here is the rope. Maybe I'll make this bigger just to make sure it's a little easier to see. And in the rope, there's a data structure called a chunk, and that is the leaf. This is implementation detail that I'll get to some other time, but it conforms to this protocol, B-tree leaf. But the important thing, the only thing we really care about right now, is what are the things that are stored on the leaf, well, on a chunk. The first thing is a string. I limit this arbitrarily to being between 511 and 1,023 bytes. 511 is there's one exception to that, which is like if the tree is of height if it contains a single node, just a root node, which is a leaf, obviously you can have less uh, bytes than 511 because you can have an empty string. Um, but in any other situation, the minimum size is 511 and the maximum size is 1023. And so I arbitrarily restrict this string to that size. I would love in Swift, as Swift does not have in like basically non-heap allocated strings. I would like to store the string or an array of bytes or whatever in line in the chunk, so you don't have to do pointer chasing. One more step of pointer chasing to get the contents of the string. But Swift doesn't have that, so I can't do it. And then here is where we start to get to interesting stuff that relates to the grapheme clusters, extended grapheme clusters that we've been talking about. So the first is the prefix count. What this is how many bytes at the beginning of this string, and this is a UTF-8 encoded string, how many bytes at the beginning belong to a character that starts on that continues from the previous leaf. It doesn't necessarily start from the previous leaf because a character can span more than two leaves. So this is basically if you were to take this string and move forward n like prefix count bytes, that would be the point of the start of the first start of a character in this leaf. And so what that means is if this is zero, that means that the if this is zero, it means there are no like the beginning of string is the start of a character. If this is the length of the full number of bytes in the string, it means the entire chunk continues a character, that is present in the previous chunk. And then we have this second thing, last char splits, which is a bool that says, does the last character in this string, in this chunk, continue on to the next leaf? And so if this is the length of the number of bytes in string, and this is true, what that means is this entire leaf contains a portion of a character that starts somewhere before on some previous leaf and ends somewhere further along on some next leaf. And the last thing we have is a grapheme breaker. This is basically, there is an algorithm for doing grapheme breaking. It is pretty complicated, I think. Let's see if we can't find it. Where are you? Okay, so grapheme cluster boundaries, bunch of definitions. All of these definitions are important to implementing the algorithm. And here's the algorithm. And I'm not even going to attempt to read it. I've read through parts of it. I haven't implemented it. It's hard. But sort of the way to think about it is you're walking forward across code points, and you have some state. And at any point, as you ingest code points and update the state, you can ask, am I at the boundary between two grapheme clusters, which would be, am I at the beginning of some character, or it could be also at the end of the string, or am I not at the boundary? If you're not at the boundary, you're within. The good news, it took me a little bit to figure this out. The good news is that you only have to move forward to do grapheme cluster breaking if you're starting at the beginning of a stream of code points. A change before, if you have, I'm not going to explain this well. Maybe the better way to say it, there were some things where I was worried that I was going to make a simplifying assumption that wasn't correct. And I don't think it's worth explaining that. I think what it is worth explaining is I sort of think about that state, the state of the grapheme breaking algorithm that gets updated as you consume consume code points. That state is kind of like a hash function. Obviously, there are many ways that it's not like a hash function, but it is like a hash function in that if you can sort of turn the crank, you can consume code points in the stream of code points over time, and you can save the state at any point, and that state is essentially represented, like it represents at some level the all of the things you've consumed, all of the code points you've consumed to that point, and that becomes useful and that becomes useful. One thing that I think is probably worth looking at that I will pull up. Where are you? Come on. Yeah, the Swift source code, because we can see the actual grapheme breaking stuff. So here, this grapheme breaker, this just wraps this Unicode character recognizer, which is it's underscored, which means it's not it's not public, but I'm using it anyway because I was definitely not going to write this code on my own. Um, and then we should be able to, in the Swift source code, find let's see, character recognizer. There we go. No, those are test grapheme breaking. There we go. All right, so this is, in this file is the implementation of that algorithm from UAX 29. But the interesting thing to look at is just get a sense of like what is the grapheme breaking state, and it kind of like even just looking at this, right? The character recognizer has whatever the most recent code point that we brought in, and Swift calls these Unicode scalars rather than code points. A Unicode scalar, I'm not gonna explain this, but I will define it. A Unicode scalar is basically a Unicode code point that is not that is from anywhere in the code space besides uh, the leading and trailing surrogate, the set of code points that represent leading and trailing surrogates, which is a hack. Uh, Basically, the leading and trailing surrogates are a hack from when we realized that we're going to need more than 16 bits to store all the possible code points. And I think that might have corresponded to when we decided that we were also going to represent all historical scripts in addition to all living scripts in Unicode. Okay, you have a previous code point because you have to, if you're going to say, is there a break between this and this, between two characters? I guess you probably have to know the previous code point, and then you have the state. Um, I guess in theory, this is all just state. Maybe you can encode it all. I'm not really sure, but looking at the grapheme breaking state, I think this is the useful thing, right? Okay, has it seen a Varama? I have no idea what a Varama is. I believe it's a feature of Southeast Asian languages. Are we in an emoji sequence? Well, are we in an index sequence? This is also uh, Southeast Asian language would be my guess. And should break regional indicate RI. RI is regional indicator, so the flag emojis that I was talking about in the last video. And so this is the state. And as the character recognizer consumes code points, or what Swift calls Unicode scalars, these booleans are updated, and then you can ask the question, am I at a break? Presumably somewhere in here. You can ask for like, here's a bunch of bytes, get me to the first break, or like consume them until we reach a break, that sort of thing. Okay, so that's what's going on with like that's a little look at the internals of like what you need to do in order to do grapheme breaking. Um, and so the question is, okay, why am I storing the grapheme breaker? Why am I storing it on the chunk? And the answer is it has to do with editing, with mutating the string. And so if you imagine, if I want to build up a whole bunch of trees where, or sorry, a tree with a whole bunch of leaves in the chunk, and it's going to be immutable, I'd never be able to edit it. All you would need to do is calculate these things, right? So as you take the full string and you start chunking it up into, approximately 1023 byte chunks, you also run a grapheme breaker across the string as you go in order to set the prefix count and last char splits correctly. And with these set, that's all we need to do in the leaves to make sure we can, in log n time index into the nth character and extended grapheme cluster. Um, the reason you have the breaker is because you need it when you edit, essentially. So for instance, I'll have to, let me open that Unicode Explorer thing that I was running yesterday. Give me a second. So this is like, yeah, let's do this, right? Let's say we have a combining acute accent. That's the only thing. It's hard to see that adding this point. Okay, obviously, I've added some spaces so we can see the combining acute accent. So this is a degenerate string in the sense that no string is supposed to start with a combining acute accent. However, it's not invalid in the sense of it can still be rendered. It is, it's not like the encoding itself is invalid. It's just degenerate in that it kind of doesn't make sense. If I were to type an A in the front, then it combines, right? Now it's an A with an accent, and and so that's sort of interesting on its own, right? And if you consider the case, if we just go back to a degenerate string, so the beginning of a string is by definition always a grapheme cluster boundary. But if I have two strings and I add them together, right? If I have one string that just contains A and one string that just contains a combining acute accent, or one rope, let's say, right? Two trees, each with a single leaf or something like that, you would assume, it's like this leaf, the leaf on the right, it's like, okay, let's say oh, whoops, how about this? A and then a space and then a U0301. Okay, so now there's a space in between these two. Oh, it's weird. It's doing some sort of, it actually, you can't see the space here. All sorts of weird things happen when you create these degenerate things. Um, I can't, I can go one after the A, but then when I go again, I go after this, and there's no way to get to the right side of the space. But if I add two spaces, then you see one space. Anyway, okay, interesting, right? Lots of edge cases. But let's say that this A is in a left in one leaf, say the rightmost leaf of the left tree, and then this combining acute accent is in the leftmost leaf of the right tree. And so those leaves are going to be, become adjacent to each other. In the right tree, at the beginning, the prefix count is 0, right? Because the beginning of a string is always the beginning of the beginning of the string is always the beginning of a grapheme cluster, by definition. And in fact, the end of the string is also always the end of a grapheme cluster by definition. And so, for instance, if you had a string that was like, just make another one, pretend this is another leaf, right? But if we have like the man emoji or some man emoji, how about this one? And then we have, this is it's going to be annoying really fast with all these spaces. And then we have a zero with joiner. Even though the zero with joiner, by definition, sort of it expects another code point to come after it. If this is the end of the string, this is the end of the string, and therefore it's a grapheme cluster boundary. And so going back to this situation where in the right string, in the right rope, the beginning is a grapheme cluster boundary by definition, and in the left rope, the beginning is also a grapheme cluster boundary by definition. When we combine these two together, when we merge them, let's say we don't, like, there are situations when, like, okay, here's, if we were actually doing this with the data structure that I've written, and you just had two strings, or two ropes, each with a single node, so a leaf, and each with one character in them or one code point in them. When we concatenated them, we'd end up merging taking the contents of the right leaf and putting it into the left leaf. So you'd end up with a string or a rope with a single node, not with two nodes, a single leaf rather than two, and that single leaf would have both the Latin small letter A and the combining acute accent. Again, ignore these two spaces. This is just because we want to have some room visually in between them. The Latin small letter A and the combining acute accent are the only two code points actually present in the example we're talking about. But let's pretend that they would not merge, right? The leaves would not merge. And one example is actually if we have like 1,000 A's, and then this combining acute accent followed by 1,000 B's. And those are the two leaves. Each leaf is greater than the minimum size, which means they won't merge. They'll just be put next to each other in the new tree, and then the tree will have two leaves. What happens then is before the concatenation, this leaf um, had prefix count of 0 because by definition, this is like the beginning of a string is an extended grapheme cluster boundary. And this one also had prefix of 0, but actually, and this leaf, the more important thing is the left leaf, last character splits was false because this was the end of the string and therefore, by definition, a extended grapheme cluster boundary. What happens is when you merge them and you concatenate them, and then these leaves are siblings, uh, we have to change last char splits on the left leaf from uh, false to true, and we have to change prefix count of the right leaf to the length in bytes of the combining acute accent, and my guess is that's 2 bytes. And in fact, we can answer that question, um, uh, which is to say, okay, 80 through 7FF are 2 bytes, and if we go back here, this is between 80 and 7FF. So indeed, the combining acute accent has 2 bytes. And so the prefix count, and imagine we had like something like this in the right leaf, or let's make it countable. So this is 2 bytes, this is a byte, this is a byte, which means the whole leaf is 4 bytes. Before the concatenation, this ought to have, and let's bring this back forward, this ought to have a prefix count of 0, and it has 4 bytes. After the concatenation, this ought to have a prefix count of 2, because the first 2 bytes belong to a character in the previous leaf, and then it still has a total byte count of 4. And then this leaf, the leaf on the left, which used to have last char splits as false, now has last char splits as true. And so we delete the spaces, except it doesn't work in this case. I can't even see the space. Okay, yeah. All sorts of weird things happen when you make degenerate strings. But, oh, whoops. There we go. Once they're merged, right, even if this is in the left leaf and this is in the right leaf, it's one character that spans the leaves, and it's another character, and we have to keep this metadata up to date. And so we need to be able to, as we perform operations, insert this string at this position, delete these things, replace this with that in a tree. We need to essentially resync the grapheme breaks. We have to make sure that they that all of this grapheme breaking state, prefix count, last char splits, in each leaf is up to date with the latest contents. And so one way to do that would be to just like redo that each time you edit it, right? Just like rerun a grapheme breaker from the beginning of the string to the end of the string, but that means each edit is now order n, which defeats the whole purpose of using a rope. And so what we do instead is we store the breaker. We store essentially the breaking state at the beginning of each leaf. So this is the state as it was consuming everything up to the beginning of this leaf. And we can, if we need to, run it forward from here. And so that means at any given leaf, we can start consuming a stream of code points to find out, where is the new, what these two things have to be updated for. And essentially what you do is you take the original state and then you take some new state, that exists because of the edit, and you run them across the string together until they're synced up, until the state, all the internal state is of both the old breaker and the new breaker is the same. And it's complicated. I'll show you what the code looks like. Here it is. So it's in this function fix up with next, which we can talk about the sort of architecture of perhaps a little later. But here you get the old breaker from the next chunk, and you get the new breaker, which is starting at the beginning of this chunk. Then we consume we have the breaker that was at the beginning of this chunk consume everything in this chunk. And so now both new and old are at the end of this chunk, at the end of this leaf, the old is at the end of whatever the leaf was previously, and new is at the end of whatever the leaf was currently. And then we start to walk forward. Um, S is the string in the next chunk, and we walk forward and we check if they have each of them have a break. And in certain situations, we say, okay, we found the same break and we're done. Or if we didn't find a break, but the graphene breakers are in the same state, we're done. And it's like complicated stuff. I wrote a lot of comments because it took me a while to get this right. Um, and this is a pain. And it's well, that's all there is to it, right? This is a pain. I'll mention one other thing, and I won't go into the details, but I feel like we've spent almost 40 minutes. We spent quite enough time on graphene breaking, and I think we're probably going to be spending an hour and 20 minutes total when you take into account the last video. But fix up with next. What I basically wanted, actually, you know what? We can probably open Swift Collections. Do we have it? Not in my recents. Uh, Developer. Swift Collections. So Swift Collections, which is Swift Collections, which is a Swift package that Apple maintains that has a bunch of advanced data structures, has a rope. What I call a rope, they call a big string, and then what I call the B tree, when what Zed calls the sum tree, Swift Collections calls a rope. Um, but the thing I was going to show you in the big string example, like if we do big string, I think append. Yes. So in each of the functions where they mutate, for instance, append, um, there is a moment where they have to, oh, I think this is actually in the ingester code here. Somewhere in here, they essentially, every time they mutate the string, they have to remember to do the resync breaks. And maybe yeah. So here's an example. Okay, here's an append function, and like do some stuff, and they call break state, and they resync the breaks, and then they call an internal append, and they save. And they're doing the same thing, right? They save the breaking state in each leaf, so that you don't have to scan across the whole string every time you do an edit. But you have to remember to call it resync breaks in a whole bunch of different places, and I didn't like that, and so what I ended up doing, which I'm quite pleased with, uh, is having a sort of fix up function. Um, in general, the way I build the way I do any sort of mutation is with this thing called a builder, B tree builder. Um, and it basically has we're not going to go into this right now, but it has a stack of stacks of partial trees, and it sort of concatenates them all together. Um, and I built into the builder a sort of a fix-up system, which is to say, uh, a leaf can say, where are you? Push, 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 push. Here it is. Push in, and then here. This is the most internal push. A leaf can say whether it needs fix-up on append. And if it does, we fix up the left and the right. And so as long as you're using this B-tree builder to do your mutation operations, which I do I don't have a practical way of doing it otherwise, so I do. You can just plug in a fix-up function that gets called everywhere. And so that's what this fix-up thing is. And I'm very pleased with this. I have some optimizations so that I believe you don't want to call fix-up unnecessarily because it takes time to run. And I believe I'm making the minimum number of fix-up calls needed in all situations. Basically the same number of fix-up calls that you'd make if you were doing it manually. All right, that's graphene breaking. It's interesting, I think. I think all of this, text layout rendering, editing things are interesting. It is complicated as heck. And I learned a lot. So thanks for watching, and I'll see you in the next one. I'm back. There's something I forgot. Uh, if this video weren't already long enough, I mentioned that this is not the only way to do things, deal with graphene clusters. And well, the what are other ways? I think if we go back and look at this tree, an obvious simplification, something nice, would be perhaps if we didn't have to store the grapheme breaking state as state, right? If it could be computed in an efficient way every time we wanted to use it. Now, I think I think there's no way to get around storing the grapheme breaking state if what you want to do is present the same interface as a Swift string, where in Swift a where a string is a collection of characters. I think you probably like if you want to be able to efficiently index and offset, go to the millionth character, you need to know how many characters are in each subtree. You need to bubble that information up in order to get the log n access property. But if you relax that restriction, if you say, well, maybe we don't have to present the same interface as Swift string, there is another way. There is a way to get away with not storing any of this text at runtime. And that is, this other technique is implemented in this Unicode segmentation crate in Rust. So it's a library in Rust that obviously I couldn't use in Swift because it lives in Rust world. But the Unicode segmentation crate has something called a grapheme cursor. And what the grapheme cursor does, I think it's so clever, it's designed it basically allows you to go forward and back, right? To iterate in both directions over a set of extended grapheme clusters. And so it doesn't give you sort of, well, it's not it's not a data structure, right? It's not like a tree that can give you log n anything, but it can allow you to iterate over in either direction. And crucially, it is designed to be used with things like with non-contiguous text storage, right? So it's designed to be used with something like a rope, where you have a whole bunch of little strings in the tree that make up another string. And, I bet it could be used in all sorts of other, it's like it could be used if you had an array of strings or something like that. Or any other sort of, way you might store a big string in some smaller strings. And the clever thing that this does is, can we find an example of using it? No, these examples don't quite have what I'm looking for, because there's like a pattern match thing. You call this provide context as boundary, next boundary. All right, it's not really here. I do know where we can find it, though. We can find it in the source code for the Xi text editor, which is sort of the original, basically the place where this sort of store text in a rope that kind of looks like a B tree, where that lives, or where that idea sort of first came from, or certainly the first place I saw it. And so, yeah, so it does not do, I think the thing, it does not try to provide a collection of grapheme clusters that you can, use the properties of the B tree to index into in a log n fashion. It just provides, well, the ability to, from a given grapheme, go to the next grapheme or go to the previous grapheme. And it does this using grapheme cursor. And this is what's cool about the grapheme cursor. It is designed to work in, it's designed to work in, with, as I said before, with a data structure that stores a big string in smaller chunks. And so what you do is you make a new grapheme cursor and you tell it the total length of the string. And you haven't given it any string data. You've just told it the offset that you are into the string, presumably in bytes. Because maybe this is actually doing UTF-8 processing. I don't know, but let's assume it's in bytes. So you give it the offset, or maybe it's in code points, right? Maybe this is the code point offset. I think from what I know of the Xi code, I bet this is a byte offset. So you give it a byte offset where you are in the string, and you give it the total length of the string. You don't give it the string. You don't give it any data. And then this is I'd like to go to the next boundary. So this is moving the cursor along the string. And what does this do? This returns a result. And then we're pattern matching on the next boundary, and we're looping. And basically, we get this graph, like if it fails, if this does not, this either will return to us the next boundary, which is a byte offset in the string, or it will return to us some sort of grapheme incomplete error and popovers. And then we match on the grapheme incomplete error. And it could be one of two things. It could be pre-context, it could be next chunk, or it could be some sort of other error and we return nil. And I don't know what other things it could be offhand. Next chunk is the simplest one, which is it's basically saying, I don't have any information. I don't have any string data or enough string data to get you to the next break. Can you give me some string data? And so, yes, we can, right? What we can do is, oh, wait a second. Where do we give it the string? Oh, no, never mind. This just says advance to the beginning of the next chunk. So here we don't actually give it the string data. So in order for it to return this error, it already has to know something about our string. But if it returns next chunk, it's basically saying there is no grapheme break. There's no next grapheme break before the end of this chunk. And so what you do is you set the position you're at to be the end of the chunk, and then you ask for the next boundary again, and then you loop again. The more interesting thing is this pre-context error, I think, because what it basically does, this is saying, I don't have enough information to tell you. You need to give me some string data, and the pre means string data before where we are, and then we provide it. And here, this PL is a string, and so we're providing this context, and we're saying, this is here's some string data. And then the second argument is the position of the chunk of the start of the chunk. Or actually, maybe it is. Yeah, that's what it looks like. Who knows? You're giving it a position, like some chunk of string, and the where in the full string this chunk exists. And so this will get returned at least once, right? Because whoops. Yeah. This gets returned at least once because the first time we ask for the next boundary, when we ask for the next boundary here, the grapheme cursor has not processed any string data. And it's possible also for it to ask for previous context more and more and more, going to the back, because let's say you're halfway through a 1 GB string and that string contains a single character or a single grapheme cluster because it's just an A followed by a million combining accents or something. It will keep asking for context further and further towards the beginning of the string until it finds a break, and then it's able to walk forward. And that is that's really interesting, right? It basically it can kind of, it's not quite running the breaking algorithm backwards, but if you remember when I was describing the breaking algorithm, it's like you're consuming a stream of code points and updating some state. And so it's not that it's running it backwards, but it like asks for chunks backwards and runs it forwards, and then asks for another previous chunk and runs it forwards. At least I think this is what it's doing. And this is, basically it's pretty clever. And especially if your characters are short, this will run very fast, right? And so you don't actually have to store all of that grapheme breaking state and keep it updated in the tree, and that's really nice. The problem is that in the sort of edge cases, right? The edge cases where you have a 1 GB string that's a single character, then it becomes order n, right? So it becomes read back the entire string to the beginning and then move forward. And this is true even for multiple graphemes, right? We were talking about the regional indicators, the flags, right? If you have a million regional indicator characters, you don't know, and you break the break between the flags is the even offsets between the regional indicator code points rather, and you have to scan all the way back to the beginning of the run of flags of regional indicators to know which are the even and which are the odd offsets. And so that's the downside to this approach, right? Which is like, okay, you don't store the state, but it means in certain, I can't remember the name. It's not degenerate. It's I can't remember. It's the certain. It's like when somebody evil gives you a string or something like that. You have to you end up with this big linear scan backwards, and that's not good. Um, the the what was I going to say? Well, I guess that's sort of it, right? So that's one trade-off is like this can lead to bad performance in the case of unusual input. And the other one is it means you can't provide the sort of Swift's string the sort of the Swift's like you can't kind of ape Swift's string interface, which is that a string is a collection of characters. Okay, now we added an extra 11 minutes to this already very long video. Now I'm done. I'll see you next time. Bye.